So we will take an example of how this 3-level page table translation actually occurs in xv6. So we'll essentially take an example of how, given a virtual address, from software itself we can use these multiple level page tables to translate a virtual address to a corresponding physical address, right, or identify the final physical page table or final physical address for a given virtual address, right. So the function we'll be looking at is present in this file called vm.c, right. The function is called walk, and it takes 3 input parameters: the page table, the virtual address, and a boolean value or an integer value called alloc, right. The page table, the first parameter, is essentially a pointer to the L2 page table. So the L2 page table is over here, and we are essentially identifying we have a pointer to this L2 page table. So given from this, we can use we want to essentially traverse the page table to the multiple levels of page tables to a specific page table entry, right. The second parameter is the virtual address. So we want to use the virtual address, use this page table, and then do the walk, right. So to move from the L2 page table to the L1 and then finally L0, right. So the third parameter is called alloc, right. So alloc is essentially used to determine whether we want to allocate a new page frame or not. If it has a value of 1, that means to say that we want to allocate a new page frame and create a new page table entry. If it has a value of 0, we just ignore it. It's more like just reading the contents of that page table entry, right. Why do we use this function walk? So one of the examples would be when we are loading the program for the first time. So we do something like /a.out, right, and this should essentially create a process, right. And as we have discussed earlier, the process would have multiple blocks, and we would at least need to have 1 or 2 blocks in memory to essentially get the program start execution, right. For that, we would need to allocate some page frames for that particular process, for those particular blocks, right. In such a case, we would essentially use alloc to be equal to 1, right. So on demand, we can essentially allocate. Now the next thing we want to essentially note is the fact that there are various other examples of where walk can be used. So if I go to the source code, right, and I simply just grep for walk, right. So we see that walk, there are multiple functions where walk is essentially used. So you can essentially look into these functions and see how and why they are essentially utilized. Okay. So now let us essentially look at what this function does. So the first 2 lines, that is this over here, checks whether the virtual address is greater than some particular value called max VA. So note that this virtual address is of 64 bits, right, but our addressing scheme can support only 39 bits, right. So that means our maximum virtual address is 2 power 39 minus 1. Okay. So so anything above 2 power 39 minus 1 is invalid, right. So what we do over here is check whether our virtual address is valid. So if VA happens to be greater than 2 power 39 minus 1, this happens to be 2 power 39 minus 1, then we essentially panic, right. So panic essentially would terminate the operating system, saying that something is not right over here. We are trying to use a virtual address which is greater than the maximum virtual address, and therefore this should not happen, right. So if we have a valid virtual address lesser than 2 power 39 minus 1, then we can essentially, yeah, so this should be 2 power 39. Okay. So this part of the loops essentially is traversing the multiple page tables, right? Starting from the L2 page table, that is the page directory, the topmost page table, we traverse page directory by page table until we reach the third level page table. So we have a level over here which is set to 2, meaning that you're starting from level 2 page table, then coming from level 1, and then finally level 0, right? So now what do we do, right? So we see over here that we are taking a defining this thing called star PTE, right? So this is your page table entry, right? So your page table entry uh, would be of this form. So it is essentially what is going to be present in each of these entries within the page table, right? And as discussed, your page table entry would look something like this, right? So it would be 64-bit, would have flag bits, would have ppn0, ppn1, and ppn2, which is a physical page number. This is of 44 bits, right? So this is defined as over here as this thing called PTE underscore T, which is your 64-bit. Okay. So page table PX level comma VA. So yeah. So what does this mean, right? So PX level comma VA, level is 2, right? The virtual address is what is essentially passed into the as a second parameter in walk. And what is essentially done over here is that this macro px level comma va extracts this value called ppn2, right? And right, and this macro is then used to index into the PTE entry. So what we have been able to do is this is essentially a page table. We've been able to get one entry into the page table, right? And yeah, so now in this line 80, we've been able to obtain one page table entry, and now we have the page table entry with these multiple bits. We check whether the bit is valid, right? So star pt and pt underscore v essentially checks whether this pt, the valid bit, is set or not. If it is set, then you know that the page table entry is valid. So you can now get the um, get the next level of page table. So what are we trying to do over here in line 82 is um, yeah, is checking the valid bit. If this bit is set to 1, then we get the 44 bits corresponding to the next level of page table, right? And then we can, in the next iteration, look at the next level of page table. Right. Okay, right, right. So yeah, so if this particular page entry is invalid, that means the valid bit is set to 0, then you come to the else part, right? And in the else part, you want to determine whether you have to perform an allocation, whether you want to create a new page table or you want to create a new page frame and so on. So if the value of alloc is set to 0, then you don't need to do any of these. But if the alloc is set to 1, then you are actually creating a new page frame, which is either used for your program, right, for your OS or to create a particular program, or it is used as a page table, right. So here this particular function called kalloc is used to create a page frame and return an address called the page table, right. And then you set the values of 0 to the page table to this new page frame that you have created, and if needed you can set the PTE bit of this new page frame you created to be equal to 1, right. So, this way you are actually going through one level, and similarly the next iteration will go to level 1, repeat the same thing. So, this would be the level 2, then you go to the level 1, you can extract the page table entry with PTE, determine whether it's valid or invalid. If it's valid, you can just return it or get the page table entry. If it is invalid, you have the choice to either allocate a new page frame for the new page table, or ignore the thing and return 0, right. And this you do for multiple levels of pages. Okay. Okay, so let's next talk about how the RAM is managed, right? So what we've been seeing so far is how your processor, your CPU creates a virtual address, and how to essentially convert that virtual address to a physical address and access a corresponding page frame. But now what we are actually going to look at is what the OS does with the amount of RAM. So we know that page frames are created, but where does a page frame, how is it managed? How does the OS know whether to allocate page 8 or page 7 to a new process, or uh, whether page 2 is needed, is used or not used, and so on, right? So to start off with, what we know is that there is a large chunk of RAM. In our example, we took RAM as relatively small. It's a 256 megabytes, right. And we can, so the RAM itself is broken down into chunks of 4 kilobytes, right. So starting from 0x, say in our example 0x 80 million, right, to 80 million plus 256 megabytes, and every 4 kb we have a new page frame, right. Okay, so the OS, so what we have now is multiple page frames in the RAM, right? And the OS needs to somehow keep track of which page frames are used, which frames are unused, where should it allocate from, where should it not allocate from, and so on. So that's what we'll be looking at as to how the operating system manages these page frames. Okay, so to start off with, the entire RAM looks something like this, right? So let's say we have the 256 MB, right? So this is 80 million, which it's called as the kern base, right? It's called as the kern base in xv6 is because at this location 80 million is where we essentially have or have the xv6 code starting from, right? The xv6 code starts from here and ends say at this particular location called end, end. Okay, so one pointer for us is this 80 million where the kernel starts, end is where the kernel ends, and physical stop is where your RAM ends, or this is your usable memory, usable DRAM memory, right. So the region between end and physical stop of physical stop is what you can the kernel can use for either creating page tables, for allocating user programs, for heap, stack, codes, anything, right. So any of the memory it wants to allocate to either for a kernel task or for a user program, it would be between this range of end to physical stop. Okay, so how does the kernel essentially manage this region, right? So what the kernel does is this particular region, it essentially splits it up into chunks of 4 kilobytes. Okay, and every time it so it um, yeah, so every time it wants to allocate a particular page frame, it would invoke this function called kalloc. This is in xv6. It will invoke a function, this function called kalloc, and kalloc would essentially pick up one of these page frames from this particular set of 4 KB frames, right? And now this page frame can be used either to kernel or for the user program. And at the end, right? So when when this program ends, or this particular page frame is not utilized anymore, the OS would call this function called kfree. Okay, so kfree essentially would free this particular 4 kilobyte chunk of memory, right? So what's really happening is that we have a fixed set of memory chunks, right? Each chunk is of 4 kilobytes. The OS utilizes a few of these chunks for some purposes, like to start programs, create page tables, and so on. And after they've been utilized, it essentially frees these chunks. Okay, so internally, to manage all this memory, the operating system xv6 creates what we call as a free list, right? So every page which is free becomes part of this free list, which essentially is a linked list. So we have the head of the linked list pointed to by this location free list. So this is the first chunk of 4 kilobytes. This has your typical linked list. This would have a pointer to the next chunk, which is this, right? Another 4 kilobyte. This would have a pointer to the next chunk, the next free page. This would have to the next free page, and so on, right? So your entire memory is split into two parts. Your entire memory is split into two types of pages. One are the used pages, which is shown in green, which is used for different purposes by the kernel or by user programs, and so on. And the second part is the unused memory, which are the free pages, right, which the OS can use at any point in time for its various tasks. Okay. Now the free pages are essentially maintained in a singly linked list. Okay. So whenever the kernel wants to utilize whenever the kernel wants to allocate a new page for whatever reason, it will look into this free list and it will pick out a page from the page frame, from the head of this page, right? So here, for instance, suppose the kernel wants to create a new page table, right? It will look into this free list, it will pick up the head, which is this, and allocate this particular page head to it will allocate this head for its purpose, right? And the way it's doing it is with the help of this kalloc function, right? Similarly, the linked list would be adjusted and so that the free list now points to the next free node, which happens to be this one over here, right? Similarly, if the kernel wants to free the memory, it invokes kfree, which essentially appends this particular linked list at the head with the recently freed page. Okay, so the free list, just to look at how it's implemented, there is a structure called struct run, and it has struct run star next. So for those of you who have written linked list programs or singly linked list programs, so you would immediately see the connection, right? So you're essentially having a structure called run, and you have a pointer called next to a subsequent structure of the same form, right? So if you want to compare this with the examples that you have done typically, right, with linked list examples that you typically run, what is missing here is the data that is present along with the linked list. So in this particular case, because we are only interested about in the memory, we don't have corresponding data. What is only present over here is a pointer to the next free page, right? So this is how the linked list would look like. The head is called the free list, and you have just one entry in each chunk. So each of this data is 4 kilobytes, right? And each has a pointer to the next free page, right? And this is a singly linked list until we reach the end where it is terminated with a null, right? Okay. So yeah, so this is what happens. So just to yeah. So, quick recollection for the booting process. Recollect that we started xv6 starts in this entry.s and then goes to start.c and then invokes this function called main. And in main, based if this is the CPU ID 0, that is the first CPU ID, there is this function called kinit, right? So kinit essentially is the function which initializes the memory, right? Essentially what it's going to do is that it's going to create this free list. So the free list, the kinit function is essentially present here. It is called from main, as we have seen. This particular function init lock, not very important for us, we'll get to what this means later on, but important for us is that we want to initialize the memory into various page frames and also initialize the free list. So this function free range is given two parameters, end and start, right? So the entire range of memory, where is it? Yeah, the entire range of memory from end to physical stop is going to be initialized with this function called free range, right? So what is this function free range? So free range takes these two parameters, pa underscore start to pa underscore end. Pa underscore start for us is just initially it's just end, and pa end is physical stop. So the range from end to start to phi stop is going to be initialized, and page frames are going to be essentially created, right? So what are we doing here? So once we in this free range, especially in this particular lines 38 and 39, we have a for loop which starts from this PA start, that is this location, and it takes 4 KB at a time because this PG size is essentially 4 kilobytes, right? And essentially invokes k free, right? So recollect that k free it adds a node into the free list. So when I do something like this, right? So I have p pointing here, right? And and I am invoking k free with this particular p, right? K free p. I am essentially inserting a node in the linked list, right? So this is my linked list. In the next iteration, I go to the next 4 KB page chunk, invoke k free on this, and therefore I would essentially get another node in my free list, right? And in this way, every 4 KB chunk from the end of the kernel memory to the phi stop gets inserted into the free list. So in other words, each page within my memory, within my physical memory, which is free to be utilized by the kernel, gets added on to the free list page, right? So yeah, so the k free function which is seen over here looks something like this way, right? So there are some sanity checks initially. So for example, so what does k free do? So it takes a physical address pa, and the idea is that this physical address should be the start of a page, and this particular page needs to be freed, right? So therefore it needs to be inserted into or added into the free list. Okay. So this statement, this line 51 over here essentially does some sanity checks. right? So first of all, it checks whether that physical address should be at the start of a page, right? So it should be a multiple of 4096, which happens to be the PG size, right? So this is your 4096. So only if the PA, the input parameter, the physical address, is a multiple of page size, can this particular page be added into the free list. Similarly, the second check that is done is that the physical address should be between end and physical stop. Why is this required? Because it is only between the end address and the physical stop where the which is essentially usable by the kernel for various aspects, right? So physical stop marks the end of the DRAM. Above this, it cannot there is no DRAM or it cannot be utilized. Below this value of below this address of end is where the kernel code and fixed data or read-only data are present, and therefore cannot be overwritten, right? So strictly speaking, if I want to free a page, these are the sanity checks which are done to ensure that the physical page that is freed is at a 4 kilobyte boundary and the address is between end and physical stop, right? So here is more of a security measure. So we fill in some junk value into the entire address. So in this case, I'm filling up ones in this in the entire page. So as it mentions, it's just to catch all dangling references, not very important for us, right? So then what we do, right? So important for us is this line, right? So we are typecasting the physical address to R, and here is where we are adding the address, the this page which we are freeing into the free list. So our free list looks something like this, right? So this is our free list pointer, and each of it is pointing to a page of 4 kilobytes, right? And now we have what we have done is we are creating we want to insert the new node into the new page into this free list, right? So what we do is this is our R, right? So we in this line we are saying R next is pointing to free list, right? And in the next line, that is line 61, we are making free list point over here, right? So with k free, we have for a given physical address, we have essentially added that physical address to the free list, right? So just to recall over here, in this function called free range, we do this invocation to k free for every page frame that is present from end to physical stop, right? So thus at the end of this particular function free range, we have every page present in the RAM to be part of the free list, right? And as needed, with the help of this function called kalloc, the operating system can utilize the page frame for various purposes. So this function kalloc, the main objective is that it would return an address void star, which would comprise of a page frame, and kalloc would then utilize this page frame or return this page frame, which the OS then utilize it for various purposes, right? So quite simple. So what we essentially do over here is we extract the head of the free list, store the pointer in this value R, and then make free list point to the next node. So what we do is again, so if I do kalloc, I essentially make cut this point here, move it here and make it point to the next node, and this page frame is what is essentially returned, right, by kalloc. So we see here that R and then the free list points to the R next, right? So the subsequent one, and yeah, line 79 and 80 are just again not essentially required. Is more of a safety and a security measure where you fill in the entire page with some junk value, in this case 5, using this function called memset, which essentially byte by byte would fill in the value of 5 into the entire page which you're just returning, and then finally return a pointer to this value of page, right? So anytime the kernel wants to utilize to create a page table, it wants to create a new stack, wants to create a new process, wants to create a new heap or anything, it would get a new page frame with the help of kalloc and then utilize it for the required purpose.